AP Physics 1, this is the second lesson in the circular and rotational motion and gravitation unit, and this is on Newton's law of gravitation. So, what is gravity? So what is it? Well, this is the answer from the NASA website. It says we really don't know. We can define what it is as a field of influence because we know how it operates in the universe. And some scientists think that it is made up of particles called gravitons, which travel at the speed of light. However, if we are to be honest, we do not know what gravity is in any fundamental way. We only know how it behaves. So gravity is known as a force at a distance because the matter producing the gravity does not physically touch the object being acted upon by the force. Sir Isaac Newton created the universal law of gravitation, and there it is. It says the force on two bodies with mass is equal to the gravitational constant times the mass of the first object times the mass of the second object. Generally, the first object might be your body and the second object would be the Earth, over r squared. Now, r is just another way of saying distance. And what they're referring to in distance, though, and the reason sometimes they do use d in books, but it's not the distance between you and the Earth surface, which is 0. It's the distance between your body and the center of the Earth. That's the center of mass of the Earth. That's actually technically the center of the mass of the Earth, and that's not exactly in the center of the Earth because the Earth's a little bit lopsided, but that's a side issue. So it's between your body and the center of the Earth, we'll just say. Sir Isaac Newton created the universal law of gravitation. There it is again. So where m1 and m2 are the masses of the two objects, such as the Earth and your body, r is the distance between the center of the mass of the two objects, and g is the gravitational constant. And you can see it's a very small number, 6.674 times 10 to the negative 11th. What those units of measure do is you'll notice on the right side the units of measure for mass are kilograms and then kilograms again. And on the bottom it's meters and meters again because it's squared. And what they do is they cancel out all the units except newtons, which is the measure for force. So everything cancels out except what you want your final answer force to be, the units for your final answer force, and that's going to be in newtons. We know that the force of gravity is given by mg. We've been using that all semester. So F, force of gravity, equals the mass of the object, and g, assuming you're on Earth, is the gravitational acceleration of 10 meters per second squared, or your book tends to want to use, your green textbook tends to want to use 9.8 meters per second squared. The two equations then can be combined. So mg equals g m1 m2 times m1 times m2 over r squared. So say that m and m1 are the same mass of the same object. Let's say your body, for example, and m2 is the mass of the Earth. Then using the mass of the Earth and the distance to the center, we can calculate g, the gravitational constant of 9.8. So there's the equation. You can cancel the m1 and the m because that's your body. And there it is. So now when you plug in the numbers, the number on top is the mass of the Earth, and I omitted the units of measure just to save space, but it's 5.98 times 10 to the 24th kilograms. This is in kilograms. And on the bottom is the distance to the center of the Earth, which is in meters. And that gives you 9.8 meters per second squared. So here's an example from 5 steps. This, Greg Jacobs presents this example as an example of what he calls semi-quantitative reasoning. In other words, it's a number problem, but one that you should be able to kind of do conceptually. All right, so a 20-kilogram rover sits on a newly discovered planet Z, which has twice the mass of the Earth and twice the diameter. So this is a question I added. What is the mass of the rover on planet Z? And you should know that it's 20 kilograms. Mass does not change anywhere in the universe. Now the question he asks is, what is the weight of the rover relative to its weight on Earth? So assume that the mass of the Earth is m2 in the formula down below, and that the distance from the center of the Earth's surface is r in the equation below. So on planet Z, the mass is 2 times m2 and the distance is 2r. So you go ahead and plug those into the equation down below, and the only thing you have to do is you square the 2r, so it's 2 squared and r squared, so it's 4r squared. And you have 2 over 4 now, which reduces to 1/2. And if you factor out that 1/2, you get that 1/2 the gravitational acceleration on Earth, gm2 over r squared. So in other words, the gravitational attraction on planet Z is 1/2 that of the Earth. So they like to ask you these kinds of questions according to Greg Jacobs, so you want to be prepared to know how to manipulate a question like this. You don't have to use the 20 kilograms anywhere in the problem. That just complicates it by adding a lot of numbers. Okay, this is from your green textbook, your online textbook. Find the acceleration due to the Earth's gravity at the distance of the moon. Okay, so there it is, the equation on the previous slide, there it is. So the radius of the moon's orbit around the Earth. So technically it's from the center of the Earth to the center of the moon, or even more technically, it's from the center of the mass of the Earth, center mass of the Earth, to the center mass of the moon. Again, both the moon and the Earth are a little bit lopsided. We won't go into why that is right now, but they are. Okay, so the mass of the Earth, there it is. It's in kilograms. I believe before I said grams, it's kilograms actually. Okay, and the universal gravitational constant, there it is. Again, I'm going to omit units of measure just to save space, but you plug them in up above, and there you have 6.67 times 10 to the minus 11th for G. M2 is the mass of the Earth, 5.98 times 10 to the 24 kilograms, and 3.84 times 10 to the 8 meters. And you crunch those numbers, and you get this. So you see it's much, much less than the 9.8 meters per second squared that we have on Earth. It's a tiny fraction of that. It's 2.7 times 10 to the negative 3rd meters per second, because gravitational attraction is a function of the distance from a planet, and the moon is 250,000 miles away from the Earth. Okay, now we're going to compute the centripetal acceleration needed to keep the moon in its orbit. That should be, ideally, when you think about it, the same as the Earth's gravitational attraction. Those two numbers should be equal. Centripetal acceleration is pointing from the moon to the Earth, and so the number should be the same as the gravitational attraction of the Earth. So let's see if it is. So the period for the moon to make one revolution around the Earth is 27.3 days. That's why a month is called a month. It refers to the moon. But we need to convert this to radians per second to compute angular velocity, because we're going to need that for our centripetal acceleration calculation. So there it is. It looks kind of long, but this is dimensional analysis. So what you're starting with is one revolution. That's one circuit that the moon goes, one time that the moon goes around the Earth, and it does it in 27.3 days. So you start with that. Now you need to convert from revolutions, that's one time around, into radians. One time around in radians is 2 pi radians. So there's 2 pi radians for every one revolution around. So revolutions canceled out, and now all you have on the top is radians, and that's going to be in the numerator of your final answer. Now we need to get the bottom from days into seconds in order to do compute the angular velocity. So we see that days is on the bottom, so we know that one day is 24 hours, so days cancels there. We know that 1 hour is 60 minutes, so hours cancels there. And we know that 1 minute is 60 seconds, so minutes cancels there. So when you go ahead and do that calculation, you get 2.66 times 10 to the negative 6th radians per second, because you see that the only units that you didn't cancel are radians on the top and seconds on the bottom. So that's the angular velocity. Now we're going to use that to figure out the centripetal acceleration. So compute the centripetal acceleration needed to keep the moon in its orbit. The centripetal acceleration can be calculated by using either AC formula, centripetal acceleration formula, this one, or the one we're actually going to use is this one. The radius times the angular velocity squared. So using that formula where omega is the angular velocity of the moon around the Earth, there it is. Now we're going to plug in our numbers. There's the radius between the center of the Earth and the moon, and the center of the moon, 3.84 times 10 to the 8th meters. And the number for angular velocity we just computed in the previous slide is 2.66 times 10 to the negative 6 radians per second. And the formula says you need to square that number. So when you do that, you get 2.72 times 10 to the negative 3 meters per second. Remember our calculation for the gravitational attraction, G, was 2.70 times 10 to the negative 3, so it's just a little bit of a rounding error that you get there because of the precision of the digits, but you get essentially the same number. So the centripetal acceleration of the moon toward the Earth is the same as the attraction due to the Earth's gravitational field. Okay, now this example comes from 5 Steps for a 5, and Greg Jacobs presents this as what he calls semi-quantitative reasoning. It's kind of a number problem, but it's one you should do a little more intuitively. So he says a 20-kilogram rover sits on a newly discovered planet Z, which has twice the mass of the Earth and twice the diameter of the Earth. What is the mass of the rover on planet Z? So you don't need to get into the 20-kilogram part. You don't need to plug in a bunch of numbers. He says that you should almost never do numbers on the AP Physics 1 exam. So what is the mass? Well, this is a question I asked. It's 20 kilograms. Be sure you remember that mass does not change anywhere in the universe. What is the relative weight of the rover? In other words, how much more of a pull of gravity does it feel on the new planet than on the Earth? That's what relative weight means. So assume the mass of the Earth is m2 in the formula below, and the distance from the center of the Earth to the surface where the rover is sitting, so it would really be to the center of mass of the rover, is given by that equation. So on planet Z, the mass then becomes 2m2, and the distance from the center of the planet to the rover becomes 2r. It's double the size, double the radius. It says twice the diameter, but twice the diameter is twice the radius. Okay, so you just plug that in. You put 2m2 in the numerator and 2r, and then you square that in the denominator, and you get 4r squared. So you see you now have 2 over 4, which reduces to 1/2. And so it's half what the gravitational pull on the Earth was in the equation up above. So the gravitational attraction on planet Z is 1/2 that of Earth. In an earlier lesson, we saw the example of a person in a turning car feeling pushed against one side of the car. So you remember this example. And this presented a fictitious force called the centrifugal force. The actual force is a centripetal force of the car turning to your right as you're looking at it. And the inertia of the person's body wants to continue taking them forward out of the screen toward you. But the side of the car is pushing them to the right. So that's what they're really feeling. They're feeling the door pushing against them, not them pushing against the door. Now, ultimately, forces are equal and opposite, but it's really the action force, the initial force, is the door pushing against them, not them pushing against the door. Now, if we imagine the person is blindfolded, they might not know that the car is moving. Now, if you've ever flown on an airplane, some of you have, you know that in mid-flight, you do not feel any sensation of motion. You could almost imagine you're standing still in the air. You don't feel a sensation of motion. So you can imagine this passenger doesn't feel any sensation of motion if the car and the road are really smooth. If the person in the car doesn't feel any sensation of motion, then he thinks a mysterious force is pushing him against the door of the car. So from his frame of reference, he doesn't know that he's moving. He thinks something's pushing him against the side. So this is because the person has a non-inertial frame of reference. So an inertial frame of reference is the frame of reference of the Earth. However, to the children looking down from above, they're not in the car or on the car. They can see it as not the passenger being pushed against the door, but the car turning so that the door pushes against the passenger. Okay, so that's what's really happening. That's the true force it's the centripetal force along with the passenger's inertia taking them forward. That's what they're really feeling. Okay, so that's called the inertial framework. So this is what is actually happening from the perspective of the Earth, and this is called an inertial frame of reference. So an inertial frame of reference is the actual forces being put on that person, not the fictitious centrifugal force that that person sitting in the car thinks is being put upon him. All right, and that takes care of this fairly brief lesson on gravitation and on inertial and non-inertial frames of reference. I'd like you to watch the videos on rolling a ball across a merry-go-round. It does something surprising, and I want you to see that it's a good example of frames of reference.